Swayam Prabha. Digital India. Educated India.
Welcome to lecture 3 of module 7. In this module we have been discussing on heat exchanger, and in this lecture we are now will briefly discuss on various types of the compact heat exchangers. Previously we have discussed about that various types of cell and tube heat exchangers and different other types of heat exchangers like double pipe heat exchanger and all. First we will start with the various type of compact heat exchangers, and then we will try to see some important issues related to heat exchangers, cell and tube or double pipe heat exchangers. Okay. So, first when we say about that compact heat exchanger, the idea behind is that that heat exchanger is compact, means that surface density is very high. That means that surface area per unit volume will be very high, and it is usually we can say that large surface area per, so we can say that for compact heat exchanger per unit volume, and it could be as high as 1800 meter square per meter cube. Okay. And then the typical compact heat exchangers are examples are plate type heat exchangers, then spiral heat exchangers, it can have two divisions. One is called spiral plate and spiral tube, and also we have seen previously also that is that finned tube heat exchanger and so on. It can continue like that. Now, most importantly we should say that plate type heat exchanger has become very important nowadays. I will refer to as PHE. Plate type heat exchanger has become very important nowadays because it is now we can say that it is the most widely used and as an alternative to the cell and tube heat exchanger. I will tell as SHE, cell and tube heat exchanger. And what happens is, if you see there in this here, you can see that this is a typical diagram of a plate type heat exchanger. You can see that these are the plates, okay, and there are 4 holes. In each plate there are 4 holes, and tubes are some fluid is coming, like you can say that there are 2 type of fluids. This is the one fluid that is going like this, okay, and then this is the other fluid that is coming out like this. Okay, so this is the way the heat exchange takes place. So it is a typical arrangement of this. We can see here that the fluid is coming, it is passing once is passing through this, so it is passing through this and then going to this, is coming here, and then it is then collected back. Okay, and this is the hot fluid is going and going up and then collected back. So this plate is acting as a barrier. There can be different kinds of flow arrangements in case of plate type heat exchangers. We cannot go in so details of this, but it's a typical example. We can see that In this case, this is one liquid, so liquid 1, it is going like this through this hole, and this is coming through this side, okay, and again it is another one like this, it is coming like this, and then it's going. So it is exchanging through the plates. The plate acts as a barrier between the two plates, and through the plates the heat exchange takes place between the two liquids, and then they are collected back. And mostly the flow is a counter current. You can see that this is the one fluid and this is the other fluid. So this, there will be a counter current action. So always the in plate type exchange, the flow action would be counter current in nature. Okay, so that way if we can say that thin cold pressed corrugated metal plates are fitted into a frame as we have shown. Okay. Now the question is that why this is corrugated? This corrugation, this metal surface is corrugated. This is to increase the turbulence again. This corrugation is to increase turbulence and thereby the heat transfer rate. Okay, that is what is being done. So this corrugation is because of that reason. And then we can see that each plate has 4 holes. So 2 as inlet and outlet of one fluid, and the other 2 for the other liquid. Okay, so this is used for that. And then in addition to this, there are some more information that we can say that this plate acts as barrier between the fluids. Okay, and heat transfer, as I told, takes place through the plate. Okay, and individual plates can have area as high as 3 meters square or higher. Okay, the corrugation determines the pressure drop and the heat transfer coefficient. As I told, the kind of corrugation, it increases the turbulence, and as we know that increasing turbulence increases the heat transfer coefficient, but at the same time it increases the pressure loss. Okay, material of construction for these kind of plates are usually it is at least the these are little costly materials are used. Lowest cost material is stainless steel. Others which can be used as material of construction are hestalloy. This is to have some information about the type of material is used. Hestalloy, then incolloy, then aluminium, brass, titanium, tantalum, incolloy, etc. So these materials are pretty costly, and these are many times used as material construction for the plates, for the plate type heat exchanger. Now the gaskets, there are gaskets as I discussed. In case of cell and tube heat exchangers, gaskets are used for as a leak proof material, and in this case of plate and plate type heat exchanger, the gaskets are usually elastomeric materials. These are used, and typical examples are nitrile rubber, then ethylene polypropylene diene monomer, neoprene rubber, silicon rubber, ethylene propylene diene monomer, etc. These are the material of construction. These are made of this. Okay, and then applications. We can say that so wide applications are there for, particularly for as a replacement, wide application replacement, as I told, for cell and tube heat exchanger in case of liquid heat transfer. Okay, and in addition to that, this is PHE plate type heat exchanger are also used for evaporation, reboiling, etc. Okay, and it allows maximum solid loading in the fluid as 40%. Okay. Now in this case there are similar to this, there are some fouling phenomena. Fouling as similar to cell and tube heat exchanger as discussed in lecture 2. We have discussed already that how the fouling takes place, and it is by depositions, by various methods. In addition to that, there will be a corrosion also, which is also important phenomena. So therefore, here in this case the fouling will be relatively less, because some cost, as we have seen, the material of construction is relatively costly materials are being used, and therefore the fouling is relatively less. And this is the figure that gives us or shows us some flow arrangements in case of plate type heat exchangers. You can see that this is a series flow. That means that from one plate it is going to the other plate, and this is going to the other plate. The hot and cold fluid, there the two different fluids. This is say one fluid 1, if we say that fluid 1, and this is say fluid 2. Okay, so hot and cold fluid, they are going, it is anti-parallel, their counter current flow is there in this case. And if we see that from one plate to this is the diagram for one plate. So this consists of one plate, this is another plate, and this is another plate. So these are the based on the different plates. Okay, so here, so they are in series arrangement, therefore it is called series flow. And then in this case we can see looped or parallel flow, you can see that it is here. There is a fluid, there is one fluid, and it is going like this way, and then in the another plate, this is another plate, and they are meeting over here and they are going out. So this is looped and parallel flow. This is parallel flow. Similarly, the other fluid is also coming as a parallel flow, and they are looped. They are finally put into in the same loop. They are coming into the same loop. So this is looped and the parallel flow arrangement. So this is a series flow arrangement. This is the parallel flow arrangement. There are two different arrangements. As I told you, that in plate type heat exchanger, the arrangement can be of different types, and this is a typical, more little bit complicated arrangements, that we can see that this is 2 pass, 5 channels per pass counter flow arrangement. There are this is 5 channels. We can see 1, 2, 3, 4, 5 channels here. Here also 1, 2, 3, 4, 5. So 5 channels per pass. This is one pass. This is another pass. You can see here. So this is called, therefore it is called 2 pass arrangement. So first it is coming like this, and then again whole things after it's merging here, then it is getting again distributed. Okay. Then so this is the first pass. We can say the pass 1, and this pass becomes the pass 2. We can say this is pass 1 and this is pass 2, because it starts from here. So the way we can see, so this is again, it's a anti-parallel flow or counter flow that's been happening, and this is very important in case of plate type heat exchanger. We should understand the flow pattern. So the first diagram, whatever I have shown here, also a similar such kind of behavior is taking place. You can see that this is a we can say this, the parallel things are happening like this. Okay, so it's a parallel flow, and they are looped into this, and they are going out. Similarly, this is coming upward. Okay, and then it's looped and going to this side. So this is what is called your this is called parallel flow arrangement between the two liquids. Fine. Now we'll see here that some advantages why the plate type heat exchangers are becoming and nowadays very much useful. So we'll write here some advantages of plate type heat exchangers. The typical advantages are, and because of that reason it's growing in use. It is growing in use because of the following advantages. What are these? So high heat transfer coefficient can be achieved, and as I told you that it's by changing the corrugation we can increase the heat transfer coefficient, and it is said that about 3 to 5 times higher than cell and tube heat exchanger, the heat transfer coefficient can be achieved. Okay. Then second part is that it is suitable for PHE, plate type heat exchanger is suitable for a close approach temperature, and this is as low as 2 degrees centigrade, which is 5 degrees centigrade for cell and tube type heat exchanger. We should try to understand the close approach temperature means, and we know that thermal equilibrium, when the two fluids are under thermal equilibrium, then there won't be any heat transfer. Thermal equilibrium means the temperatures are same. So there should be a differential temperature between the two fluids when they are approaching towards the same directions. So this is called approach temperature. So approach temperature should be there. Should be a substantial amount of difference in the approach temperature will be there. In case of heat exchanger, cell and tube heat exchanger, it is usually 5 degree, and it should be at least 5 degree. It could be more than that. Then only you will get a good performance. But in case of plate type heat exchanger, this can be as low as 2 degrees centigrade. That is what is very important point. And then plate heat exchanger, as we have seen, that is the simple plates are being placed over there. So in case of plate type heat exchanger, easy inspection, cleaning and maintenance possible. Okay. Then we have some more important, that heat transfer area can be adjusted by changing the number of plates. Okay. So, if we require more heat transfer area, we will put more number of plates. If we require less heat transfer area, we will put less number of plates, and also we can change the plate area also. So, this is one very important, and this adjustment can be, I should say that it can be easily done. Okay. And then sometimes it is possible that two or more steams can be handled at the same time, at the same instant. So, it can be so designed that two or more, okay, two or more streams can be heated or cooled, okay, in the different sections. So, by changing the sections, we can use even more than two fluids to be heated or cooled. So, this is one uniqueness of this particular plate type heat exchanger. In addition to that, there are some more advantages, that is less floor space is needed. Naturally, it is a vertical upward, so less, it is a compact one, less floor space is required. And then we have plate type heat exchanger offers low hold up volume of fluids, and then the costs are, or rather cost is less, even though costly materials are used, and this is with respect to cell and tube heat exchanger. Okay. Now, so this is all about a plate type heat exchanger. So, we can understand that plate type heat exchangers are nowadays people are using, and because of certain advantages, and we have seen that the various advantages that it can have. Now, in addition to this plate type heat exchanger, there are some more compact heat exchangers which are being used, and I will just briefly tell a few things about those heat exchangers. And like for typical one is that, as I told you, the spiral plate or spiral tube heat exchanger. This is also a typical compact heat exchanger. In this case, what happens is there are this is also the flow is, in this case also it is a compact heat exchanger. Then it is suitable for handling viscous fluids and slurries. Then it's of a reduced fouling rate, fouling is less. Then it can be cleaned easily. So, we have to see the operational point of view also. This fouling is less, that cleaning, easy maintenance, these are basically operational ease. We have to see the operational ease also. We have to see the construction point of view. The spiral heat exchanger is difficult to construct, but it's operational. There could be some operational ease, but there are some difficulty in construction. In case of spiral heat exchanger, what happens is, it's like that two plates spiral, when you have considered the tubes, two concentric tubes, and they are making coils like this, and spiral plate, so two concentric channels, okay, and they are coiled. Okay. So, So, the one fluid is just adjacent to the others, and that it continues in the form of a coil, okay, like a centrifuge. So, it's like a coil, and this continues. But so this maintenance may be easy, some cleaning may be easy, but the difficulty is in fabrication of spiral plate or spiral tube heat exchanger in comparison to cylinder tube heat exchanger or even plate and frame heat exchanger. Okay, but spiral tube or spiral plate heat exchanger would be much more compact heat exchanger, we should say. Okay, so what happens in this case is that pair of, particularly for spiral plate, pair of concentric passages are coiled, okay, and one is for hot fluid and the other one is for cold fluid. There will be some concentric passages of the fluids. So, first hot, cold, like that. The same fluid will first take hot fluid, and then it will take a passage, then will go to the cold, then the next region, and then it will be accompanied by the cold fluid also. Okay. And similarly, that pair of concentric, in place of concentric passages, in case of spiral tube, it will be a pair of concentric tubes. Those will be used for flow of these fluids in the spiral tube heat exchanger. And in case of spiral tube heat exchanger, that it has got some advantages, as I told you, that the advantages of this is that in the case of spiral tube heat exchanger, that it gives the fouling is less, fouling is less, as we have discussed, and then it can use the viscous fluids, and it is always being done in case of it can use viscous fluids and can be designed for low flow rates also, can be designed for low rates. And the spiral tube or spiral plate heat exchangers are always counter current in nature. The two fluids are counter current in nature of flow. So, their flow nature will be counter current. Okay. So, now in addition to this spiral tube heat exchanger, there is another one which already we have discussed previously. There is the fin tube heat exchangers are also there. In this case, the tubes are having some fins, and these fins can be, these are called, this is, you can see this are lateral fins, and this is the circumferential fins, and these are circumferential fins. You can see that it is a radial, or it is also radial or circumferential, whatever you say. This is a rectangular profile, and these are circular tubes with transverse. These are transverse fins or longitudinal fins. Fins. So, longitudinal fins are used here in case of cylinder tube heat exchangers. There are certain aspects that has to be taken into consideration, and while using this kind of fins. So, the aspects are that fin height, fin efficiency. Already we have discussed these issues. Okay. Then spacing between fins. So, this is basically the overall design of fin tube this is again that fin orientation. So, overall design of the fin tube will decide, it will decide that pressure drop, it will decide the heat transfer coefficient, and then depending upon that we can use this, as we have discussed that rate of heat transfer Q is equal to Q dot is equal to U A delta T, and this, as I told in the last class also, last lecture, last lecture, that U is the overall heat transfer coefficient, delta T is the temperature, and I is the area of heat transfer. When the fluids, particularly that airy substances, air, say in case of say if we have to extract energy from air, heat energy, or if we have to cool some body, then what happens is that air to metal surface heat transfer coefficient is, air or vapor or any gaseous substance to metal surface heat transfer coefficient is very small compared to the liquid side one, and therefore what happens is that the rate of heat transfer becomes less, because if you see the rate of heat transfer depends upon the area U and delta T. Delta T, as I told that previously also, that it cannot be cannot be independent, it is decided by the external world, and U, there is a maximum value of U that can be obtained by changing the flow rate. So, making the very high flow also, you can make some maximum amount of U that can be obtained, and also there is a flow rate limitations that we have to, the cost of pumping or cost of compressor, all these things has to be taken into considerations, and then what stays in our hand is that area. So, by increasing the area we can increase in the heat transfer rate, and which is being done in case of heat transfer between an airy substance and surface, as I was telling, and this the fin tube heat exchanger is normally being done for this kind of applications, where the surface area of the tube surface area or heat exchange surface area is dramatically improved, increased, and then heat transfer rate accordingly gets increased up. Okay. So, this is about the different types of compact heat exchangers which are usually being used, and now we will come to one more type of heat exchanger that is called a regenerator. So, what is being done in this case is that it is basically a heat transfer between two streams passing by passing the hot and cold fluids alternatively through a bed of solids. So, we have a bed of solids, it's like this. So, say this is we have a bed of solids here. This we can say bed of solids, and then the streams are passed. It can be counter current, it can be co-current, usually it is a counter current. So, from one side one flow, say this is, if I say the fluid 1, and then other fluid is coming like this, this is the fluid 2. So, this is fluid 2. So, when fluid 1 is coming, if I draw in the other way around, it will be like this, say. So, it is like this. If I say this is F1 and this is say F2, in that case it will go like this, and then here also exactly the similar way. If we draw, it will look like this, say this one and this, it is say F1 and this is say F2. I am sorry, both cannot be like that. So, here I will make little changes. So, it is like this. So, F1 is going this side, and so this is F2, F2 has to come from this side. So, this is F2 and this is F1. So, this is F2 and this is say F1. So, if F1 is hot fluid, F2 is cold fluid. So, hot fluid is coming in and is becoming colder, and it is here, it is leaving the energy and this becoming warmer, and then once it is done, then that from the other end this fluid is F2 is coming, which is a cold fluid, is coming in, and then it is taking the energy and going away like this way. So, this kind of utilization of the energy, particularly for the cases of say extracting thermal energy from flue gas. Okay, so flue gas comes out at a high temperature. So, what it can be done? It is placed through this packed bed, and so the packing material should have some substantial amount of the heat storage capacity. So, that should be the property of the packing material. It's a good heat storage capacity. Okay, the packing material should have appreciable heat storage capacity. Okay. And what happens is that then what advantage we are going to, but what advantage? So, there are some advantages we are going to get, and in this case is that high surface area, because finer particles, there will be huge solid surface that is being there in the packed bed. So, high surface area for heat exchange, and they are easy to clean, and then easy to replace also. That packing materials if destroyed or if needed can be easily replaced. Why if needed? Because if we want to change the packing material because of depending upon the amount of heat capacity, heat storage capacity. So, this can be done. So, now this is, as I told you, this is very good for use for the gaseous substances, particularly it is a rotary, it can be static or it can be rotary regenerators. Are widely used in electric power plant. Okay. But this is not suitable, this is very important, not suitable for liquids. There are many reasons behind that. First of all, the thermal conductivity of liquid in pores would be similar to that of solids. That is one thing. So, therefore, the heat exchange would be a difficulty, and then the mixing, that is the major problem between two fluids. Is always there. So, it is better if we can, so that cannot be, a mixing cannot be avoided, this can't be avoided. So, it can be, so this thus that regenerative heat exchanger could be good when the two fluids can be separable, and the mixing won't be a problem for cases. Okay. And the effectiveness of such heat exchanger, it is like a packed bed, and it depends upon on number of transfer unit, and cycle time. How many times it is being used. So, that is also very important thing, and the number of transfer unit is defined as U overall heat transfer coefficient. A is the area by C. C is the heat capacity. It is m dot into C. For m dot is heat capacity into mass flow rate. This is the total heat capacity, and this is the specific heat capacity. This is the total heat capacity. This is equal to C, and this is for hot fluid or cold fluid. So, this capital C, you can say that is equal to m dot into C. M dot is the mass flow rate and C is the heat capacity, specific heat capacity. So, this is becoming the heat capacity, okay, per unit time. So, and UA by U is the overall heat transfer coefficient and A is the area of heat transfer. This is called a number of transfer units for such situations. Okay. So, this is about the different types of some aspects on different types of heat exchangers that are normally being used in case of heat transfer operations. Some of them are very commonly used, like double pipe. It is not double pipe, like selective heat exchangers, and some of them are very important and upcoming, like plate type heat exchangers, spiral heat exchangers. These are very upcoming heat exchangers, and they are replacing the selective heat exchangers in many situations. Okay. Now, some important aspects now related to the driving force for heat exchange we would like to discuss here. So, some issues related to flow pattern and driving force. We will discuss this. So, first of all, let us consider, say, a double pipe heat exchanger. In case of double pipe heat exchanger, that there can be a two type of flow pattern, as we have discussed. This is a perfectly co-current and perfectly counter current we have discussed. So, co-current and counter current. Okay. Already we have seen it, but if we say that this is the length and if we say that this is the temperature here, the profiles, if we draw for co-current, the profiles appears to be like this and it appears to be like this. So, we can say this is the approach temperature. So, this is the maximum possible approach temperature. So, it can be at least 5 degrees centigrade or even more than that. This is the co-current case, and we can say that in a double pipe it is a perfectly co-current or perfectly counter current situation. So, this is the hot fluid, this is the cold fluid. Fine. Now, the question is that we know that LMTD also we can find out what is the, because we have seen that in both the cases that delta T gradually changes along the length of this, delta T gradually changes. So, here it is delta T1 if I say, and this is delta T2. In this case, this is delta T1 and this is delta T2, as because they are gradually changing, and we have seen already that for parallel flow and counter flow there will be some both the cases that the driving force is being given by LMTD, log mean temperature difference, and LMTD is nothing but delta T1 minus delta T2 by ln delta T1 by delta T2. So, this is what is the driving force for that. Now, the question is, it's a very common question that we can have. We all know that counter current is better performing. Counter current is better performing and counter current heat exchanger is preferable. The reason behind this is that if you see, first point is that the in case of counter current, the outlet temperature of the hot fluid doesn't decide the outlet temperature of the cold fluid. So, we can increase the cold fluid temperature even more than the outlet temperature of we can increase the outlet temperature of the cold fluid even more than the outlet temperature of the hot fluid. So, that is not restricted, that is the first point. And second point is that if we see in case of the co-current, the delta T is gradually changing. Initially it is very high and later on it is very low. So, it is a non-uniform, but in case of counter current heat exchanger, it is an uniform distribution of the driving force is always there, and that gives a better performance of the heat exchanger. So, these are the two important aspects that we should keep in mind, and therefore, that counter current heat exchanger is always preferable. In most of the situations, it is preferable than the co-current heat exchanger. Second point, what I wanted to say over here is that when we consider about the multi-passes, then what happens? Say consider the two case, 1-2 pass SHE, cell and tube heat exchanger. First consider this case. So, what happens in this case? If we just quickly draw, okay, this is the cell and tube heat exchanger is the cell side. So, this is say TH, okay, and this is TCA, that is the starting point, and it is a 1-2 pass. So, it is like this. So, this is the I am sorry, and then there should be a nozzle over here. This is the hot fluid start and hot fluid out. This hot fluid in, and this is THB, and this is say sorry, TCB. This is TCB and this is TC in. Okay, and then I will write as TCA. So, TCA. So, what happens is we can know that it comes like this, okay, and then it goes like this, and then it comes like this, and then goes out. Okay, so this is the flow directions of the cold fluid, and the flow direction for the hot fluid is that will come like this, and then it goes like this. So, therefore, in this region we can see in this region it is counter flow, and this region it is parallel flow. Okay. So, in a 1-2 heat exchanger, and there in the two the fluids, the tube side fluid will once it will encounter as a counter flow, and another time it will encounter as a parallel flow. So, that is very important to decide that where we should put. Should we put the tube side here and then cold fluid the entry here and output here, or entry here or output that side? That is very important. We need to maximize the driving force for the heat exchange. Okay. And if we draw it like this way, we will find that it is like this, sorry, and it does not merge exactly. So, this is not correct. So, we should draw like this. Here it exactly matches, and then so this is the case, okay, and this and this. So, this is becoming TCI, and here it is say TCA, this is TCB cold fluid, and this is THA, and this is THB. So, what we can see here that from TCA to TCI is the parallel, TCA to TCI and THA to THB, THA to THB and TCA to TCI, these are in parallel, and this is in counter. So, in the counter flow is the hot portion of the hotter side or hot fluid of the hotter part of the cold fluid, and this one is in counter flow, and the other side is in the parallel flow operations. So, now what we can say here in this case is that it is neither a perfect, so in this case it is neither a perfect parallel flow or nor a perfect counter flow situations. So, under perfectly counter flow there can be something LMTD, or under perfect parallel flow there will be LMTD, but it is not neither a perfect parallel flow, neither a perfect counter flow. So, how to get the values of the log mean temperature difference for this system? Actually, what is being done in this case, that we have to find out this is the delta T, maximum possible delta T, and this is the maximum possible delta T1 and delta T2. So, we have this, and based on that we will calculate LMTD, will be delta T1 minus delta T2 by ln delta T1 by delta T2. But this is not the actual scenario in the heat exchanger. There will be a lot of changes, and that is taken care of by a factor or by a plot. This is called a plot of correction factor. That correction factor takes care of this issue, and to give it and to give a average value of LMTD, log mean temperature difference, and this is obtained. There is the correction factor versus some temperature ratio, and that is plotted for some parameter. Okay. So, this temperature ratio, correction factor versus temperature ratio for certain parameter in case of L type heat exchanger, that for this is for 1-2 heat exchanger. Similarly, 1-2 cell and heat exchanger, there can be for 2-4, for different passes there can be different such plots. These plots are available in several literatures. This can be followed, this can be used to find the values of the correction factor, and that is must to find out the correction factor. And correction factor is, if I say here now, say I will say that correction factor is Ft, and so its maximum value is Ft, maximum value of Ft equals to 1. Okay. And so actual average LMTD is Ft into LMTD, or I should say average LMTD, not actual average. LMTD is this Ft into LMTD actual. Okay, based on that configurations. So, now what happens is in this case that ratio, there are two things are being there. Temperature ratio, that is the x axis, it is nothing but we say that it is equal to R, and that is equal to TCB minus TCA. So, this is the cold fluid higher hot temperature, cold fluid inlet temperature, outlet temperature, cold fluid inlet temperature minus by THA minus TCA. This is the maximum temperature difference between the cold and hot fluid. This is the cold fluid entry temperature, the hot fluid entry temperature. So, this is the maximum difference, temperature difference. So, for multipass heat exchanger, we use correction factor, and correction factor or Ft is used to get corrected LMTD, and so LMTD corrected is equal to LMTD into Ft, and LMTD is delta T1 minus delta T2 by ln delta T1 by delta T2. That is what, as we know, and with these values of correction factor we have to calculate from the figure as I said, and there are two parameters are there. One is the temperature ratio, that is the x axis, it is R, and this is equal to TCB minus TCA by THA minus TCA, and you can see that it is the cold fluid outlet temperature minus cold fluid inlet temperature. So, the differential temperature between the cold fluid, and this is the maximum temperature difference in the heat exchanger, like the temperature difference between the hot fluid inlet and the cold fluid inlet. So, this is the temperature ratio, and that parameter P, and that is given by THA minus THB by TCB minus TCA. So, it is that differential temperature of the hot fluid by differential temperature of the cold fluid that is being achieved by the heat exchanger. So, based on this parameter, we have several values of the correction factor, LMTD correction factor. So, like this way we have to use for even for 2-4 passes or 1-4 passes, different passes of heat exchangers, we have to consult the respective charts and find out the values of LMTD correction factor and then go for the calculations of the heat exchanger area. We will take up some problems later on in some subsequent lecture and see how to use this, and then I will ask only a simple question, say that first question is that if the driving force delta 1 to E1 is equal to delta 2, whether it is a parallel flow or counter flow does not matter, if the driving force delta 1 T1 and delta 2 are same, then what is LMTD, or what would be the temperature difference that should be used, temperature difference that should be used. This is a very common question, as we know that LMTD expression, why the question comes, LMTD expression is delta T1 by delta T2 by, it is delta T1 minus delta T2 by ln delta T1 by delta T2. So, when delta T1 is equal to delta T2, so LMTD becomes 0 by 0, that is undefined. So, we need not bother about this LMTD because it is undefined and we need not bother about it. What we can understand is that when both sides driving force are same, then what we will say is that the actual driving force is delta T1 is equal to delta T2 is equal to delta T. We will use the same driving force for that. And second point is that when we have say in case of heat exchangers, if we have say linear driving force, exactly linear driving force, say this is delta T1 and this is delta T2, and if it varies linearly, there is no nonlinear variations. If it is possible, then our driving force will be delta T will be equal to delta T1 plus delta T2 by 2. That is all. A simple arithmetic mean we should use. So, we should use the arithmetic mean when there is a linear variation of the driving force. We should use the same driving force when there is no more change in delta T, in both the sides the delta T is the same. Then also there is a linear arithmetic mean also will do, and when there is a non-linear variation, then we should make use of LMTD or log mean temperature difference. And another thing also I should point out over here, that when there is a condensing steam in a Swayam heat exchanger, condensing steam means that the hot fluid, so steam is used to heat a cold fluid, and steam is just losing the latent heat of vaporization to heat the cold fluid. So, condensing steam when it is used on the cell side and tube side, there will be a cold fluid which is used up, which is taking up that latent heat, latent heat from the no sensible heat, only the latent heat from the fluid, and that situation it remains the co-current or counter current remain the same, because if you see the temperature profiles, it will become like this. Temperature profiles, whether it is a co-current or counter current, does not give any difference, it will remain the same. So, if I say this is the condensing steam and say this, so both the times, both the cases, the delta T remains the same, because this is becoming the reference frame, and the reference frame is the stagnant, there is no change in the reference frame. Therefore, whether it is a counter or co-current, that does not create any differences. Okay. So, this is all for today. I will stop over here, and next class we will see to find out we will do some calculations to find out the heat exchanger areas or design of the heat exchanger. Thank you very much.